27,000 light years from where you are sitting right now, something is flickering. Not steadily, not predictably, randomly, like a heartbeat that refuses to find a rhythm. At the exact center of our galaxy, a supermassive black hole, 4 million times the mass of our sun, is doing something astronomers did not expect. For years, scientists assumed that once you understood the rules of a black hole's accretion disk, the chaos would eventually settle into a pattern, a rhythm, a signature. It didn't. In 2024 and 2025, the James Webb Space Telescope pointed its infrared eyes at Sagittarius A star for 48 hours, spread across an entire year of observation. And in every single session, the black hole did something different. No 2 nights alike, no repeating cycle, just constant, restless, unexplained flickering. And one of those flickers, recorded in April of 2024, was unlike anything ever caught on camera before. So, the question that should follow you through this entire investigation is simple, and it's one that has haunted astrophysicists for decades. How can something like this exist? I'm Captain Vega. I've spent most of my life staring into data that comes from places human eyes will probably never reach. And if there's one thing the galactic center has taught me, it's this. The closer you look at the heart of the Milky Way, the less it behaves the way it's supposed to. Let's go there together.
Nobody knew yet what it truly was. It took decades of patient, almost obsessive observation, tracking individual stars as they whipped around an invisible point in space at astonishing speeds, before scientists could say with confidence what was hiding there. By the early 2000s, teams led by Andrea Ghez and Reinhard Genzel had measured stars orbiting that invisible point so fast, so tightly, that only one explanation remained possible: a black hole, roughly 4 million solar masses, compressed into a region smaller than our solar system. That work eventually earned them the Nobel Prize in Physics. But knowing something is there is very different from understanding how it behaves. And for that, astronomers needed a telescope that could see in wavelengths no ground-based observatory could reliably capture: infrared light that slips through the dust clouds blocking our direct view of the galactic center. That telescope is the James Webb Space Telescope. Here's the first mystery. Black holes themselves don't emit light. Nothing escapes past the event horizon. What we actually observe is the accretion disk, the spiraling storm of gas, dust, and superheated plasma being dragged toward the black hole before it crosses the point of no return. That disk is where the fireworks happen. Using Webb's NIRCam instrument, a team led by astrophysicist Farhad Yousefzadeh at Northwestern University watched that disk almost continuously. And what they found unsettled a lot of assumptions. The black hole wasn't just producing occasional dramatic flares. It was constantly bubbling, faint flickers happening every few minutes, punctuated by brighter eruptions, with no periods of true rest.
We observed the black hole multiple times throughout 2023 and 2024, Yousefzadeh explained, and we noticed changes in every observation. Think about that for a moment. Every time Webb looked, the story was different. That alone raises an uncomfortable question. If the activity is this chaotic, this unpredictable, how much do we actually understand about the physics happening just outside the event horizon of our own galaxy's black hole? Now, before we go further, if mysteries like this one keep you up wondering what else is hiding in the dark corners of the universe, this is exactly the kind of investigation I love sharing. Stick with me, because the next revelation is the one that made headlines around the world.
And it certainly doesn't mean solved. Then came April 6, 2024, the night that gave this investigation its name. For the first time in the history of astronomy, scientists using Webb's MIRI instrument detected a genuine mid-infrared flare erupting from Sagittarius A star. This wasn't a wavelength range anyone had successfully captured from the black hole before. It lasted roughly 40 minutes, and remarkably, radio telescopes on the ground, specifically the sub-millimeter array, picked up a matching signal about 10 minutes later. A delay, a real, measurable delay between the infrared burst and its radio echo. Why does that matter? Because it means scientists, for the first time, could trace how the flare physically evolved, watching high-energy particles emit light first in the infrared, then cool and shift into radio wavelengths as they moved outward, exactly as theoretical models of magnetic reconnection predicted they should. Sebastiano von Fellenberg of the Max Planck Institute for Radio Astronomy, lead author on the study published in the astrophysical journal Letters, called it a missing piece finally falling into place, evidence connecting the different wavelengths of light into a single physical story about how the black hole's environment behaves. And yet, here's the part that keeps astronomers uneasy. That one clean, well-behaved flare sits right next to dozens of others that refuse to follow any predictable pattern at all. This is where competing ideas enter the picture, and I want to be honest with you, none of them are proven. Some researchers have spent years hunting for periodicity, a repeating clock hidden in the chaos.
One analysis of nearly 900 days of gamma-ray data proposed a possible 96-minute quasi-periodic oscillation, alternating bursts of roughly 78 minutes of activity with about 18 minutes of quiet. If real, that kind of rhythm could hint at something orbiting extremely close to the black hole, or oscillations in the inner accretion flow itself. But other, more direct infrared observations, the very ones from Webb, have so far found no consistent periodicity at all. Just noise, just chaos, dressed up occasionally in something that looks like order, then dissolving again. Some astrophysicists lean toward pure stochastic turbulence, random churn with no hidden clock. Others argue we simply haven't watched long enough, that patterns this subtle require far more continuous observation time than we've managed so far. The Northwestern team themselves said their next goal is a full 24 uninterrupted hours of Webb time, specifically to settle this question. Personally, I've always found it fascinating how the universe resists our need for tidiness. We build models, we expect symmetry, and then something like Sagittarius A star looks back at us and simply refuses to behave. So why does any of this matter beyond our own galaxy? Because Sagittarius A star is, in a very real sense, humanity's laboratory for understanding every supermassive black hole in the universe. It's close enough and quiet enough compared to more violent, feeding black holes in distant galaxies that we can actually study its behavior in fine detail. Magnetic reconnection, turbulence, particle acceleration, physics that likely governs black holes billions of light years away that we could never observe this closely. And there's a strange new relative to consider.
These are dramatic, repeating X-ray bursts from supermassive black holes elsewhere in the universe, and their underlying mechanism is still fiercely debated. Comparing that erratic behavior to what Webb sees at our own galactic center might eventually reveal whether there's a shared physical thread connecting black holes across the cosmos, or whether each one truly is its own unpredictable beast. That's the real mystery, isn't it? Not just what's happening at Sagittarius A star, but whether chaotic is simply the true hidden nature of every black hole once you finally get close enough to watch it breathe. We still don't know if the flickering hides a rhythm science hasn't found yet, or whether unpredictability is simply written into the fabric of how matter behaves at the edge of oblivion. Every observation Webb sends back adds another piece. But for now, more pieces mean more questions, not fewer. And maybe that's exactly why I keep coming back to places like this. Some mysteries aren't meant to be solved quickly. They're meant to humble us, to remind us that even our most powerful telescope, aimed at the closest supermassive black hole in the universe, still can't tell us the whole story. If you want to keep exploring what's hiding in the dark corners of our galaxy, there's another investigation waiting for you. One about the strange, glowing objects called the G objects, orbiting dangerously close to this same black hole that shouldn't be able to survive there at all. Some mysteries are connected. Let's go find out how.